Hi guys, I'm Becky, Science Tutor, and today we're going to explore the hot and cold side of chemistry, the endo and the exothermic reactions. So have you ever felt the heat from a burning candle, or noticed how an ice pack gets cold by itself? These are perfect examples of energy that is being released or absorbed during a chemical reaction. So in this session we're going to break down what these reactions are, how to spot them, and why the energy changes occur. And so let's dive in. Okay, so an endo and exothermic reaction. If we think about first of all the names of these reactions, and we'll break them down as we go. Okay, so an exothermic reaction. If we think about EX, that is something that is exiting that reaction. Thermic is referring to the heat. So if we have an exothermic, this is a reaction that is giving out heat. So like our burning candle. So exothermic, we have energy released. Okay. Now the way that we would detect an exothermic reaction is that we would notice an increase in temperature. Because as that heat energy leaves the reaction, it's heating up the surroundings, and therefore we detect that temperature increase. Okay, now I've already given you a common example of a burning candle. So anything burning, any combustion reaction, obviously we know that they get hot. And if we're thinking in terms of more chemical reactions that you may carry out in the lab, we've got things like neutralization. And if we think a little bit more biologically, we have got respiration. But respiration is releasing the energy from the sugars that we ingest. Okay, on the flip side of that then we've got an endothermic reaction. So again, if we break down that word, N-E-N, enter. So the thermal, the heat is entering the reaction. So endothermic, that means that the heat energy is coming into the reaction. So here we've got that the energy is being absorbed. Okay, so how would we detect that? Well, we would notice a temperature decrease because the thermal energy from the surroundings is going into the reaction and therefore leaving the surroundings feeling cooler than they were. Okay, and again let's give you some examples. So the reaction that we talked about in the introduction, we're talking about those ice packs getting cool. So what happens in those, like those sports injury packs, is that you will break a membrane. Usually have to squeeze the bag pretty hard. You'll break a membrane between the two solutions. They will mix, and that will cause that temperature to decrease. Okay, so things like uses is when we want to cool things down. If we think about the opposite of respiration, thinking biologically, if we think photosynthesis, probably going to get in my way. Sorry, just budge myself out of the way a second. So photosynthesis, because the plant is taking in that energy in order for it to carry out the photosynthesis, because it's almost like the reverse, isn't it? Yeah. Another one that is often used as an example is thermal decomposition. And again, if we break down that word decomposition, breaking down and it's thermal decomposition. So we're breaking down using heat. Okay, so let's have a look then at the reaction profiles. So lots of questions dig into what is going on inside the reactions. There's kind of 3 levels to this. Now, if you are a foundation or a higher level student, knowing what is going on and being able to draw, recreate and label these reaction profile diagrams is key. If you are a higher level student, we will dig a little bit deeper into actually what's going on in terms of bonds. Okay, so we all need to know how to interpret these reaction profile diagrams. So let's have a look at what's going on. So across the bottom you can see we've just got the progress of the reaction. So start to finish. Now in an exothermic reaction, so take note of the labels at the top, in an exothermic reaction, the reactants have a certain level of energy. Now the reactants in the exothermic, they have a higher energy than the products. So if we look at where the line has come down for the products, that is lower than the reactants. Now in terms of being able to label these up, we're going to look at some questions in a minute. There's lots of variations that they might give you. They might ask you to label the reactants. If you're asked to label the reactants, it's simply just writing reactants. You don't have to worry about what's going in. But obviously at the start of the reaction here, we're going to start with the reactants because that's all we've got. And then towards the end of the reaction, that's where our products is going to be. So what you'll notice here is that because the products have a lower energy than the reactants, they must have given that energy out to the surroundings. And this is how we know it's an exothermic reaction. So simply by just looking at where are the reactants, where are the products, which one's higher, which one's lower, we can work it out. Because if we look on the reverse then, let's look at the endothermic reaction. Our reactants at the beginning of the reaction are lower in their energy than the products at the end. So for that energy to have increased, energy must have come in to the reaction. So things that you need to be aware of and things that you could be asked to label onto the diagrams. So on our x-axis is simply just the progress of the reaction. We're starting with the reactants, there's a bit that happens in the middle that we'll come to next, and then we get our products. Up the side on our y-axis is our energy, or sometimes you may see it termed enthalpy. Okay, meaning the same, it's the amount of energy that's in the reactant. Now this bit in the middle then, so here we've got the peak. So this part here you can see that what happens is that the reactants have to gain some energy first to get to the peak of this, and then it decreases. So what this is, so from where it began to the peak of the graph is our activation energy. Because we have to put a certain amount of energy into the reaction to get that going. And if you think about any type of reaction, yeah, it might be that we simply just stir the reactants to get the reaction going. We're just giving it a bit more energy by mixing them together. It might be that we have to heat them. When you strike the match to burn the candle, you're generating that little bit of heat to get that reaction of that combustion of the match going. Okay. Now you might be asked to draw a second line on this where the energy, the activation energy is lower, and we're going to come more onto that in the next session where we look at the use of a catalyst. So just to talk through the endothermic reaction, again we've got the same labels on the axes of the graph. We're going to start with the reactants first, it's just that they need to be lower. products need to be higher, but we still got the point here. So the point from there, we've got our activation energy. Okay, so I'm kind of going to clash with that other arrow, but it doesn't matter. So the activation energy is going to be all the way down because we've had to put all that energy in first to get that reaction going, and it's just give us a bit of energy back. So we've put in all that energy first to get it going, and we don't get as much back. Therefore, we're kind of almost in an energy deficit, and that's why we feel a temperature decrease, because it's taken that energy in. We haven't got as much back out. Okay, so make sure you know those labels and you can sort of regurgitate those labels and label those up on some examples. So I'll show you some examples next. I'll show you a couple of different levels of styles of questions of what you need to do. So here you can see we've already got our X and Y axes labels on, the progress and the energy. Now it tells us that it's between ammonia and oxygen. It has labelled up the actual sort of numbers. So we've got 4 NH3 plus 3 O2. Doesn't matter for that. What we're looking for here is it asks us to complete it by labelling the activation energy and the overall change. So remember, activation energy is how much energy you've got to put in first to get that reaction going. So that would be, this is the level of energy that we start with. This is what is already in those reactants, and what we've got to do is we've got to take it up to that peak first of all. So this is our activation energy, and our second one is to label the overall energy change. Well, we had to put that much energy in first to get to the peak of the graph, but then we're given that back out. So the up and the down bit, overall, there's no change. So our overall change, if we just track that across so we can see where we're at, our overall energy change would be from where we started down to our products. So this would be our overall. Okay, so you see how it's important to know what these labels are, what this little graph is telling us. Okay, let's take it up a level. So here we've got 3 marks. So this time we have to complete the profile line, label the activation energy and the overall energy change. So first of all, we've got to know, well, what type of reaction is this? It tells us in the question that this is an exothermic reaction. So the energy of our products is going to be less than our reactants, so we need to bring that down. Now there's no set, obviously you can see there are no values on that y-axis. It doesn't matter how much you come down as long as you kind of make it obvious that they are lower, yeah, but nobody's going to measure it, and it's not that it's got to be 3 centimeters lower or anything like that. And then we're just going to bring that line down so that it joins our products. So we've completed the profile line, label the activation energy, so these are what we've done before. So starting from our reactants up to the peak, that's the energy that we've got to put in. Okay, and if we're thinking about the line, it's gone up, we've put our energy in, that energy has come back out, so therefore if we track across from our products and we come down from our products, down from our reactants down to the products, this is our overall energy change. Okay. And a third and final one then, so this is describe. So we've just been completing those diagrams in this one. This one we are asked to describe the errors. We've got to be able to interpret it. We've got to know what it should look like so that we can pick out where those errors are. So let's have a look at what information we've got. So it tells us that the reaction between hydrogen and oxygen releases energy. Okay, so a student drew a reaction profile, for the reaction between hydrogen and oxygen. Okay, and it says that the student made 2 errors. So when it's exothermic, when it's releasing the energy, our products should be lower than our reactants. Okay, so that is one of the errors. So we can say something like the products needs to be lower than the reactants. And remember, it doesn't matter if you kind of word it slightly different. It's when a mark scheme is used, it's usually termed its ideas around. So as long as you're showing that the products are explaining that the products need to be lower than the reactants, it doesn't matter if you don't use it word for word as mine. That is absolutely fine. Yeah, don't panic about that. Okay, and the second error, so let's have a look. Well, the activation energy doesn't come from the products, it needs to come from the reactants. So the activation energy, yes, they've drawn that diagram wrong, but even if that was for a endothermic reaction, if they had drawn it correctly, then your activation energy still needs to come from your reactants line. Okay, so we're going to have a look at bond energies then. So this is now for higher tier level students only. So if you are a foundation student and you know for certain that you are going to be sitting the foundation paper, you don't need to worry about learning about the bond energy calculations. And if you have any questions on what we've just done in the session previously, then please do comment on the video, pop me a message through the platform, or however you want to contact me, and I will help you out with those questions. Right then guys, so those of you that are doing higher tier will need to be able to do bond energy calculations. So here we're digging a little bit deeper into what is going on. Where does that energy come from? Where does that energy go to? Okay, so in a reaction, what happens is that bonds are broken and then they are reformed. Okay, now I've got some little models here which just by chance is good, because you can show you these. So this is like a little model of oxygen's oxygen O2, so it's got some bonds within it. Now if I want to use those oxygen atoms in another product, if I want to change it, then what I need to do is I need to break these bonds. Perfect example, having to put that energy in to break those bonds apart, because I want to use, throw them around my desk, I want to use these individual oxygen to attach them to something else. Okay, so what we need to remember is that bond breaking takes in energy from the surroundings, whereas our bond making, okay, let's grab something different so you can see we're adding it to something else. So if I was going to add that hydrogen to my oxygen, when I then reform that bond, when I start to make those bonds again, bond making releases energy to the surroundings. So I've got to put the energy in, but I get some energy back. And basically it's the difference between how much energy did you need to use to break those bonds compared to what did you get back. Okay, so you have to be able to do some of these calculations. Just noticing there's a 3 marks under there. So what I'm going to do is I'm going to guide you through one of these questions. Now with these questions, it is just about being methodical, taking your time, making sure that you don't miss any of the bonds. Now most questions give you what I call the displayed formula up here. So you can see these physical bonds. And a tip from me would be to cross off those bonds when I've put them into your calculation, so you know that they are done. Okay? So what we're going to do is we're going to work out how much energy was used in bond breaking. Whoops. So we'll do our bonds broken, and it's always minus our bonds made. Okay, so all we're going to do is we're going to work through methodically, well, what is broken. Okay, so you can see here we've got a hydrogen to a nitrogen. So there's 1, 2, 3 bonds that I need to break within that nitrogen molecule. And we need to be careful because there's a 4 in front of that. So I've got 4 times that molecule, so I've got 4 times 3. Yeah, so we've got 4, 8, 12. So we're going to have 12 times, and then let's look it up in the table. A nitrogen to a hydrogen is 391. Okay, and we're going to add that because we've also, remember, it's everything before the arrow. We've got oxygen to oxygen. Now it's a double bond, but that's fine. It's given the double bond in the table, so we just need to make sure that we're breaking through those. And we've got 3 times that, so we're going to add that to 3 times 4, 9, 8. Okay, so then add these together. So I'll slow this down a little bit. Have a go with me. And when you're doing things like this, it's what works best for you. You might want to do the 12 times the 391 first, get that answer, then do your 3 times 497. It's just about working it really methodically. Like I'm putting it in my calculator now using brackets, and I almost missed a bracket. Yeah, so maybe it would be better if I'd have done it separate. So the bonds broken, I've got 6,186 joules of energy. Now I'm going to do exactly the same for the amount of bonds made. Okay, so I've got 2 times, so that one's nice and easy. I've just got 2 times the 945. And then I've got a hydrogen to oxygen, I've got 1, 2, but I've got 6 of those molecules, so overall I've got 12. So I'm going to add that to 12 times 464. And I'm going to add that together. Okay, and for that I get 7,458. Okay, so that's your first step. Bonds broken, bonds made. Now the equation is always bonds broken minus bonds made. Okay, so we're going to do 6,186 minus 7,458. Now what tends to happen here is that students type this into their calculator, and you can probably see that we're going to get a negative number, and then students panic because they go, oh, I've got a minus number, so I've got minus 1272. Okay, but that is fine. A negative number just shows that that energy has come out of that reaction. Yeah, we're down by that energy, and therefore what that means is that because it's showing us that we got more energy back out than we did than when we broke them. So it gives us more energy out because that's our 7,000. We got 7,000 out and we only put 6,000 in. So that's just showing us that that is an exothermic reaction. But don't worry too much about that. If you can get to a point where you can do these calculations, it's always bonds broken minus bond made. And don't worry that it's a negative number. Yeah, that's my key thing there. Don't panic if you get a negative number, that's fine. Roll with it. And then we've got the little follow-up question. Explain why it is exothermic and use the values from your calculation. So this is where we want to be saying that we got more energy out by making bonds. Yeah, so however you do this, so I might say that I got 7,458 kilojoules was released when the bonds were formed. And only, say only, but it's less than, only 6,186 kilojoules was needed to break the bonds. Yeah, so here you're just showing, break the bonds, you're just showing that you know that because it is a negative number, that is a exothermic reaction because we got more energy out. It was bigger what we got out than what we had to put in, and therefore we must have that energy being released. Okay, so these calculations are a little bit tricky, so my hints and tips are to you, as I've done up there, cross them off when you've included them in your calculation so you know that they are done. Watch out for any multiples of compounds. This is quite a higher level question. I've gone right in at the deep end with you so I could show you everything in one, and just do it methodically. If you need to work out bonds broken and bonds made down a separate piece of your exam paper and then just put your final workings out like I have, that is absolutely fine. Separate them so you know exactly where you are, because otherwise we get lots of numbers and we get ourselves jumbled up. Okay then. And again, if there are any questions surrounding these, you want any more practice, you're not sure on what to do with them, then obviously just comment on the video or into the platform, and I will get back to you. I'll see you next time.